Hello everyone! You may have seen this picture in one of the slide decks. We have finished with the ground floor of the signal processing building and continue to the first floor. The next 4 lectures are all about Fourier transforms. You may be wondering why this topic is so important. Well, there are 2 reasons for this. The Fourier transform makes the calculation of convolutions much more efficient in the case of long impulse responses, and it also facilitates the analysis of all kinds of signals. Efficient convolution using Fourier transforms will have to wait until lecture 6. To give you an idea of where we're going, this figure shows that, thanks to the discrete Fourier transform, the computational complexity n log n of the approach shown in the lower half is much smaller than the direct computation of the convolution in the upper half with complexity n squared. The analysis of signals using Fourier transforms will be the main storyline of today. This lecture is about the usefulness of the Fourier transform in general and the Fourier series in particular. Welcome to the Essentials of Signal Processing, lecture number 4. Let us start with the basic idea that we are after with Fourier transforms. The crucial observation is that we humans are very good at recognizing all kinds of patterns. For example, when we think of speech and music, we never think of individual samples, but always of tone, pitch, or frequency of such signal. We say that somebody has a high-pitched voice or that basses are low. Also in many other fields we tend to view phenomena as periodicities or frequencies. Consider for example electrocardiograms, vibrations of structures such as bridges, and periodic seasonal changes in the weather, traffic and economy. It is clear that we humans are just good at understanding the world through the lens of frequency patterns. In that context, it is relevant to realize that our cochlea, the inner ear of our hearing organ, converts sound waves into neural signals through an analysis of frequencies between a few hundred Hz and 20 kHz. For visual information, such as pictures, we rely on 2-dimensional patterns like lines, edges and planes. Neurobiological studies have shown that signal processing in our retina also performs frequency analysis, in this case in a spatial sense. If you were to dive into the core of modern image and video compression methods, then you will see that those properties of our visual systems are highly exploited. Let us consider a simple example that shows the power of thinking in terms of frequencies. Any idea what this signal is? What it represents? How it sounds? Probably not, as it is very difficult for us to interpret the signal samples directly. Now look at this diagram calculated from the signal using the Fourier transform, called a spectrogram. Horizontal time, vertical tone or frequency, and the color represent intensity or amplitude of a certain frequency at a particular point in time. Any idea now? Probably you do. Now let us listen to this signal. I think you can easily correlate what you see in the spectrogram with what you hear, a whistle with increasing frequency. Here's another frequency sweep and its visualization as a spectrogram. If we take a signal consisting of a single cosine, these figures become even simpler. Looking at a cross-section of the spectrogram at a certain moment in time, we get a diagram at the lower right. This so-called amplitude spectrum shows the digital frequency horizontally and the strength of cosines at each frequency vertically. By the way, note the horizontal axis in this diagram and remember that digital frequencies are relative numbers with, for the radial frequency, a maximum of pi. If we take a more complex signal, like my current speech, the diagram looks like this. The changes over time are essential for calculating features used in speech technology using so-called MFCCs. By the way, don't this kind of diagrams remind you of the background that you have been looking at for the past lectures? So humans are very good at interpreting visualizations of frequencies in signals. Now the question is, can we come up with a mathematical analysis of signals that captures this idea? Not surprisingly, the answer is yes, namely the Fourier transform. Its inventor, Joseph Fourier, continues to have a profound influence on modern digital technology. Living in the Napoleonic era, I'm sure he could not have predicted the long arm of his theoretical work. In developing the Fourier transform, especially the one used in practice, the discrete Fourier transform, I have two options. The first is that I give you the DFT equation and the Python function and you just use it. In that case you can calculate the DFT of, for example, this short signal of 8 samples. But I believe this approach leads to no insight into the resulting numbers and becomes just a trick. That is not what I want to achieve in this course. I want you to understand what these DFT numbers shown here actually mean. The second and preferred option is therefore that I show you where the DFT is coming from. So even if you never use the Python function, you do not lose the concept of Fourier transforms. But that's going to take a bit of time and actually requires a detour through continuous time signals. So that is where we start on our way to the equation of the week. Let us consider this periodic continuous time signal. In later lectures we will drop the requirement of periodicity, but for now that is what we need. This signal can be decomposed into 4 sinusoidal terms. For each cosine we have a frequency, for instance 15 Hz or 105 Hz. A strength or amplitude, for instance 1.5 for the cosine with frequency 15 Hz. And a phase, or if you like, a position relative to TU0, for instance pi/4 for the frequency 75 Hz. In Fourier transforms we are given the signal and we try to find out which frequencies occur, with which amplitude and which phase. We plot the result in a so-called amplitude and phase spectrum. The amplitude spectrum that you're now looking at is a simplified version of the spectrogram I showed earlier. Now, in this field it is common not to think of decomposing a signal into cosines, but into complex exponentials. Just to remind you, this is Euler's equation that tells you how to interpret the complex exponential e to the power jx. It is important to realize that the complex exponential is a number on the unit circle in the complex plane with magnitude 1. Here are some examples of often used values of x. By combining e to the power jx and e to the power minus jx, we obtain the expression for the cosine of x. We can now rewrite a continuous time sinusoidal signal in the following way. It is important to understand the two essential parts of this equation. First, the complex exponential omega 0t and minus omega 0t, which are now functions of time. We can visualize these complex exponentials as so-called phasors in the complex plane. First, e to the power j omega t, for f is a quarter or omega is 2 pi f, is half a pi. Then for the negative omega, and finally the combination of both. The red arrow represents the real valued part of the phasors, in other words, the continuous time signal that we are analyzing. Second, this term represents the amplitude and phase for frequency omega 0. This is the polar representation of a complex number with amplitude a/2 and phase phi 0. Remember, that is what we want to plot in the amplitude and phase spectrum, as shown here. Note that we have not only the amplitude and phase of the positive frequency omega 0, but also those of the negative frequency minus omega 0. For real valued signals, which we consider in this course, the amplitude and phase spectra always exhibit this complex conjugate symmetry. By the way, these diagrams show radial frequencies. You can always rewrite this in terms of Hertzian frequencies because omega is 2 pi f. If we can write a single cosine in this way, we can also do it for 2. Here's an example for a signal with frequencies 100 and 250 Hz, each with its own amplitude and phase. We can also visualize this as rotors. You see the 4 complex exponentials resulting from a signal with 2 cosines, with frequencies in this case of 0.3 and 0.9 Hz. Also note the different amplitudes and the phases, here expressed in degrees instead of the usual radians. From here we can go to n cosines. With a bit of bookkeeping, we rewrite the resulting sum of complex exponentials in this form. Note that the negative frequencies here correspond to negative values of k, and that ak and a minus k are complex conjugate. For an arbitrary periodic continuous time signal, we may need an infinite number of complex exponentials. To this end, we make one more step by relating all frequencies to their greatest common divisor, or fundamental frequency. As a result, each frequency is now a multiple of the fundamental frequency. The reciprocal value is called the fundamental period. Putting this in the equation, we end up with what is known as the Fourier series or Fourier synthesis of an arbitrary periodic continuous time signal. And that is the equation of the week. It tells you that, given a periodic signal, you can always write it as a sum of potentially an infinite number of complex exponentials, each having a Fourier series coefficient ak. And from these ak's we can calculate the amplitude and phase spectrum. For instance, for this signal the fundamental frequency is 10 Hz, the greatest common divisor of 20 and 30. And the fundamental period is 0.1 second. So the Fourier coefficients are these. And this is what the resulting amplitude and phase spectrum looks like. For a more complex signal like this square wave, we can also find the amplitude and phase spectrum, shown here. It is interesting to see what happens if we manipulate the coefficients of the Fourier series. For instance, if we keep only a0, a1 and a-1, this is the expression and the waveform that we get, which is like an approximation to the original one. If we use more of the Fourier coefficients, we get a better approximation of the original waveform. Of course, to go back to the original, we need all of the Fourier coefficients. At this point you may have wondered how I got the Fourier coefficients for this more complex signal. And indeed, I have not gone into that so far. So the question is, how do we carry out the Fourier analysis on arbitrary signals? Let me first explain the core idea. If we try to find out if a cosine with a particular frequency occurs in a signal, then we can try to match that cosine to the signal and see if it fits. Here's an example for the simple signal that we started with. If we take a cosine with frequency 15 Hz, then the match looks like this. Now if we multiply and integrate the signal and overlay cosine, we get a number that is directly related to the amplitude of the cosine of that frequency. If we take, however, a cosine of a frequency that does not appear in the signal, for instance 60 Hz, then multiplication and integration will yield a number very close to 0. The mathematical details are a little more complicated, but essentially this is what Fourier analysis does. With this integral, we can compute each of the ak's. If you look at this equation, then you clearly see the multiplication and the integration of the signal with, well, not a cosine, but a complex exponential of frequency 2 pi k over the fundamental period. This integral gives you for each value of k, in other words, for a frequency equal to k times the fundamental frequency, the amplitude and phase of the Fourier series coefficient. In the case of the square wave, this integral is quite easy to solve, even by hand. For more complex signals, we may have to rely on numerical methods. In conclusion, the learning goals of this week are: first, Fourier transforms are a great tool for understanding what is happening in signals as an alternative to directly working with the sample values. Second, an arbitrary periodic continuous time signal can be written as the sum of many complex exponentials with different amplitudes and phases, the Fourier series coefficients. Third, we visualize the Fourier coefficients through their amplitude and phase spectrum. Fourth, from a signal you can compute the Fourier coefficients using the Fourier analysis equation. And finally, from the Fourier coefficients, or equivalently the amplitude and phase spectra, the signal can be reconstructed by the Fourier synthesis equation. But finally, this result is not yet very useful to us, because Fourier series deal with periodic continuous time signals. So we need to take more steps in the next lecture to make it applicable to arbitrary discrete time signals. I will end again with two exercises that you should be able to solve with this week's theory. First, given this continuous time signal x of t, rewrite it in the form of a sum of complex exponentials and plot the amplitude and phase spectrum. Second, given this continuous time signal xt, find the Fourier series coefficients a0, a1 and maybe a2 by solving the Fourier analysis expression. Well, that's it for this lecture. Good luck and see you again at the next Essentials.